Hey boys, welcome to the screencast for section 4 of our course on acceleration. You should have a hard copy of this in front of you, and as we go through and describe it, talk about it and fill in the gaps and do stuff, then obviously you're following along as well. Okay, the aim of this is to do kind of three things. We want to look at what acceleration is and how to calculate it. We're going to look at what it actually means if something's accelerating, what are the conditions it needs, and lastly we'll get on to you guys doing some examples. So we'll do some examples, and then it's like you guys getting on with doing some questions in your notebooks, which is where you'll do most of your learning. Okay, so first of all, like, what is acceleration? If you copy this down, what we say, of course, acceleration is it's simply a change in velocity. Okay, a change in velocity. So speeding up, slowing down, or changing direction, because remember, velocity is a vector. So we use that little delta V, and with respect to time. So as time passes, if your velocity changes, then that's acceleration. Okay, quick little one before we move on. That delta, what that means is a change in whatever we're talking about. Okay, we'll put that in brackets there. So like delta T could be a change in temperature, delta V, change in velocity, change in momentum, a whole bunch of stuff. All right, so acceleration, first of all, it's positive. That's what we'll call it, positive acceleration, obviously, when the velocity increases. So say, for example, you've got something like, plus 4 meters per second squared. What that means is that every second, the velocity is increasing by 4 meters a second. So if you put your foot down on the car, or something's accelerated by a slingshot or a tennis racket or cricket bat hitting a cricket ball, whatever it might be. So positive is when your velocity increases. Conversely, of course, negative acceleration is when the velocity decreases. That's what we, of course, call deceleration. Okay, so that's when, of course, as time goes by, your velocity is decreasing. A good example of that is like when you chuck something up in the air. If we say upwards is positive, the acceleration is negative, so it's downwards. And here on Earth, it's 9.8 meters per second every second. That's how it slows down. Okay, and we'll just put there, that's gravity. In both cases, if something's going to accelerate, it's always going to be an unbalanced force. Okay, so no matter how many forces are on something, if they all add up to zero, then the thing's not going to accelerate. If it's moving, it'll stay moving. If it's stationary, it'll stay stationary, but it's not going to accelerate. Okay, so what we're saying here is, in other words, i.e., in other words, that sum of the forces is not zero. If you want acceleration, the sum of your forces is not zero. And remember, in the last couple of units we talked about the sum of the forces. Another word for that is the net force. They mean the same thing. Right. What do all your forces add up to in the end? There you go. All right, let's move on and look at calculating calculating acceleration. Here's our formula we've got, and let's look at what it means. Our acceleration is our change in velocity, remember that delta V, over time. So delta V is you should be able to get this one easy, change in velocity. T, of course, is the time. Time's measured in seconds, and if we go back a little bit, change in velocity, that's going to be measured in meters per second. If we look here, our change in velocity can be expanded to v take u. And v is the final velocity. In other words, the velocity of the object when you've finished observing or finished measuring it. U is the initial velocity, so the velocity of something when you first start measuring it. Okay, I always like to remember it. U comes before V in the alphabet, so U is the initial, V is the final. What that's meaning there by V take U is like, what is it now compared to what it was when you first started measuring? All right, that's that V take U. Now, what we can do is, of course, we can manipulate this formula. As it is written there, acceleration is your subject, but we can tweak that and we can make our final velocity the subject. Okay, put a little arrow there. We'll put a little dot. We can say, well, your final velocity, how do we tweak that formula? It's going to be u plus a t. Right. And then, of course, if we want to make our initial velocity of the formula, it's so the subject is v take a times t. Easy. Right. So these are your three versions of the same formula that we'll use. It's probably not a bad idea. Highlight those, because then they'll stand out quite easily. All right. Let's look at continuing on with the dot points here, guys. Next one is acceleration. It's measured in, here's the units, it's kind of weird. m/s/s, also written as ms to the -2. What that means, of course, is meters per second per second. Remember, it's the rate of change of velocity, so it's how fast your velocity is changing in meters per second every second, which is meters per second squared. If you're not sure about that, this video attached on here, the Eureka one, explains it reasonably well. Okay, if you want, now's a good time. Pause, watch the video, come back. Okay. Next important point is, remember, acceleration's a vector. So, of course, you need to state magnitude, and you need to say which way is it pointing. Up, down, left, right, north, south, east, west, whatever it might be. And then, of course, don't forget, you got to have your units as well. Okay. So, next one here is that the direction of the acceleration, whatever that may be, also shows the direction of that resultant force that made it. Okay. So, say for example, if you apply the brakes on the car, the resultant force is backwards. It seems weird, I know, but even though it's moving forwards, the net force or the resultant force is backwards, and so your acceleration is backwards, i.e. deceleration. Okay, so whichever direction the net force is in, that's the way the thing will accelerate. What we're going to deal with in this unit is uniform motion. Things like a ball rolling down a ramp, falling through the air. For example, if you drop a ball and it falls due to gravity. So in that case there, the acceleration when things fall through the air is what we call g. And 1g is an acceleration of 9.8 meters per second squared here on Earth. And on the moon, it's like 1.6, and it depends on what planet you're on as well. All right, let's have a look at a couple of examples. The first one's pretty straightforward because it doesn't actually involve calculating an acceleration. Step 1, read the question. Step 2, in terms of working, we'll call it step 1. Write down what you know and what you don't know. So in this one, it's moving from stationary to 4 meters per second south. Stationary is your initial, 4 meters per second south to your final. What's your change in velocity? So u is 0. meters per second. The final velocity is 4 meters per second south. Delta V, not sure. Right. And if we looked at our equation at the top, delta V is just V take U, what it is now compared to what it was before. It's stopped. Okay, sorry, V, yeah, my bad. V take U. Our final velocity is 20. Okay, initial velocity was 0, and there's no overtime, so it's 20 meters per second, and because it's positive there, we call it south. Okay, V take U. All right, that one's easy. Let's have a look at another example. Step 1, read the question, pause if you need to, read the question, come back. Okay, so in this case here, we've got a car, it was moving at 20 meters per second, and all we've got here is forwards or backwards. So we'll say forwards is positive. Okay, it was moving at 20. The final velocity was 0 because it comes to a stop. Okay, it's hit the wall. How long did that acceleration take? Only took 0.8 of a second. So here's the question, what's acceleration? Step 2, you go, all right, how will I solve that? So a statement of intent, if you like. A is V, take U on T. Right, our final velocity is 0. Our initial velocity is 20, and it took 0.8 of a second. So 0 take 20 is negative 25 meters per second squared. So we've got the acceleration, check. Here's the next one. What does the negative sign tell us? Okay, the negative sign tells us two things. Okay, first of all, that it's, of course, it's not accelerating, it's decelerating. In other words, it's negative acceleration. And as a result, like the overall force, or you might call the net force, or the sum of the forces on the car, okay, are of course backwards. It's slowing the car down. So if I draw a kind of diagram, of course, there's our brick wall. Okay, crashes into a wall. The car's going to end up something like a big crumpled zone. There's our car. I'm clearly not much of an artist, but there's our car here, our gangster car, and it was going forwards. It's hit there, and the net force on the car is backwards. It was going forwards, but the force applied by the wall on it is, of course, backwards. Okay, is backwards. So that's what that's telling us. All right, let's go next one. A sprinter accelerates at 2.5 for 1 second, reaches top velocity of 9. What's her initial? So step 1, read the question. Step 2, write down what you know and what you don't know. So her acceleration was 2.5 meters per second squared. It's positive, so she's getting faster. She's accelerating for 1.1 seconds. Final velocity is 9. And we want to know, what was she doing when we first started observing pardon me, or measuring. So our statement of intent, A is V, take U on T, and if we go up to our other equations, we want our final velocity, U initial velocity is V take, acceleration times time. So final velocity was 9. Her acceleration to 2.5. She was accelerating for 1.1 seconds. So she was going 6.25 meters per second when we initially started measuring. Okay. And then, of course, just as an aside, kind of how fast is that? If we divide by 3.6, that gives us, multiply by 3.6, that gives us her speed in kilometers an hour. So she was going about 22, just over 22 k's an hour when we first started measuring. Okay. All right, let's move on. Obviously, next one is read the question. Pause, read the question, and we can come back and solve that one. So you've got an aircraft leaving the ground and accelerating at a certain rate. So we know the acceleration, 3.8 meters per second squared. We know our final velocity is 150 meters a second. How long did it take? It was 25 seconds. We want to know at what velocity did it take off. So what's our initial velocity? It's not zero, it's question mark. So essentially kind of, if here's the runway, if it took off there, accelerated up, and when we're measuring it now, it's going at 150 meters a second, which is about 700 k's an hour, I think, 650. Okay, how fast was it going like there when it took off? So just the same as the last question, really. Initial velocity is v take, a times t. Remember that little dot means times, just a shorthand. So it's going 150 now. It was, so it did accelerate at 3.8 meters a second for 25. So it would have been going at 55 meters a second on takeoff. Notice equal signs underneath each other and underline the final answer. Okay, same again. If we want to know, well, how many k's an hour is that? Times by 3.6. That gives us just under a takeoff speed of just under 200 k's an hour, which kind of makes sense. All right, let's have a look at the next one, which gets a little bit harder. Pause, read the question, think about it, and we'll start solving. Okay. So, a ball is thrown upwards. Here's our key. It reached the top of the flight after 1.5 seconds. Okay, I'll draw a diagram, a rough diagram. Here's the ground. Okay, and the ball might have been thrown up from there, and it's gone straight up and come down again. I'll draw it like a bit of a parabola just so we can see the upwards and downwards path. So it's caught again there. The thing to remember is, this is key here, and I'll highlight it. What was its acceleration? As soon as it's left your hand, the force of gravity is what's accelerating it. Okay? So what is its acceleration? Our acceleration is due to gravity, and it's downwards at 9.8 meters per second. Okay? What that's assuming is that upwards is positive. That plus with a VE just means positive. Cool. Right. So now, what do we know? We know our time is 1.5 seconds. We know the acceleration. We can just write g if we want to, because g means down at 9.8 meters per second squared. Okay, you can just write g. Now I forgot to highlight that, didn't I? Go back. There. Okay, in these examples, whenever anything is thrown up in the air As soon as like the ball leaves your hand, the tennis ball leaves the tennis racket, the cricket ball is no longer in contact with the cricket bat. If you hit it straight up, its acceleration is straight down. In fact, it doesn't matter where you hit it, its acceleration is straight down if you ignore air resistance. But we'll save that for year 11 and 12 physics. Right, so let's get on with part 2 now. With what velocity was it thrown? All we know is T and A. But, so what we're trying to find, of course, is the initial velocity. If we go U is V, take A, T, remember A is gravity, times. We know G, we know T. What we don't know is the final velocity, but we do. If we look carefully at our diagram, if it leaves the person's hand here, it goes up, and when it reaches the top of its flight, for that brief moment, its final velocity is 0. Okay, that's at the top of the object's flight. Vertically, its velocity is 0. So, with part 2, it says it reaches the top of its flight after 1.5 seconds. At the top of the flight, the final velocity is 0. And get rid of that. So, our initial velocity is the question mark. So, we can go minus, final velocity is 0, minus, negative 9.8 times 1.5. Okay. Now, the negative and negative number, of course, is positive. So 9.8 times 1.5 gave us 14.7 meters per second. And because that's positive, that makes sense. It means it's thrown upwards. So we know we've done the right thing. Because that way is positive, upwards is positive. We got a positive answer, it's thrown upwards. Okay, that's the hardest part. The next thing to remember, part 3, how long will it be in the air before it gets back to the same point? What it's saying is our displacement. Remember, S is the symbol for displacement. Displacement in the vertical direction is 0. In other words, its takeoff point and landing point are both at the same height. So, if it's taken 1.5 seconds to get up to the top, clearly it's going to take 1.5 seconds to get down because all the conditions are the same. So, we'll simply write TOF for time of flight is twice what it took to get to the top. 30 seconds. Okay, so it's a pretty easy way to work out. You can work out how fast you can throw like a cricket ball up in the air. All you got to do is time how long it takes to come back down and for you to catch it again, and you've got a pretty good indication of how fast you've thrown it. Okay. Right, like it says now, time for you guys to get cracking with some practice. Please, like it says, do these in your notes. Sure, the first few are easy, you can probably do them in your head, but you need to do these in your notes, okay, your exercise book. What I will do is maybe go through perhaps 1, maybe 2 questions before we finish up. What I might do is I'll do an easy one, and then I'll work through them, and I'll copy the answers. I'll put the answers on our OneNote here next to the questions. So if we do look at question 1, easy stuff. What's acceleration? A. So there's question 1. A is equal to V, take U on T. Okay. got up to 24 meters per second. It's from a standing start, so our initial velocity is 0. That's a little keyword that you'll come across a fair bit. It's from a standing start, and it took 6 seconds, so obviously its acceleration is positive, 4 meters per second squared. All we know is that it's positive, so it's accelerating. Okay. Like I said, I'll put the working for a few other questions up here as well. All right, get stuck into it, and our aim is to get up to, in course 2, our aim is to get up to question 20. You'll see how the last few are those sorts of questions where something is thrown up into the air and comes back. So course 2, question 20, course 1, we certainly want to be able to go that extra distance and do some of the harder ones as well. Okay, finish with a quick dad joke because I'm a dad. Why did all the baked beans move to Queensland? Because they like living in cans. All right, thanks boys. Cheers.